Welcome, everyone. This is the first screencast in our series on natural language inference, or NLI. This is one of my favorite problems. What I'd like to do is give you a sense for how the task is formulated, and then situate the task within the broader landscape of ideas for NLU. As usual, we have a bunch of materials that would allow you to get hands-on with this problem. The core module is nli.py, and then there are two notebooks. The first introduces the three data sets that we'll be exploring in detail: SNLI, multi-NLI, and adversarial NLI. And the second notebook offers a bunch of different modeling approaches. It really covers core approaches that people have taken to NLI in the past, and I hope it points to some avenues for modifying those architectures, possibly in the service of developing an original system for a final project. There's also an associated homework and bake-off. I emphasize that this is not required for us this quarter. I'm mentioning it because I think the problem is an interesting one. It's a word entailment task, which is an interesting small-scale problem that I believe could be used to stress test an NLI system in interesting ways. The core readings cover the three data sets that will be in focus for us. And then the final reading listed here was, I think, the paper that introduced attention mechanisms into the study of NLI, and that had an impact that went well beyond this task. And then for additional readings, I'm kind of suggesting a range of things. Some of these readings cover core fundamentals for deep learning that I think will be useful in the context of studying NLI. Some of them help you with kind of a foundational understanding of the NLI task and how you might think about it. And then some of them are meant to kind of push us to stress test our system, think adversarially, and maybe find artifacts in our data sets. And those are going to be themes of later screencasts in this series. To begin getting a sense for how the task is formulated, let's start with some simple examples here. So in NLI, we have as our inputs a premise sentence and a hypothesis sentence, and the task is a classification one. So in this simple example here, the premise sentence is a turtle danced. The hypothesis sentence is a turtle moved. Both of those are system inputs, and our task is to assign one of three labels. In this case, the correct label would be entails. The second example looks simple, but it actually begins to suggest how the task is actually formulated. We have as our premise turtle, and as our hypothesis linguist. And what we would like to do in the context of NLI is assign that the contradicts label. Now you might pause there and think, it's not a logical fact that turtles can't be linguists. So surely contradiction is too strong, but it is a common sense fact, a kind of natural inference about the world we live in, that no turtles are linguists. And it's for that reason that we would choose the contradicts label. And that begins to key into the fact that fundamentally, NLI is not a logical reasoning task, but a more general common sense reasoning task. Every reptile danced is neutral with respect to a turtle ate, which is just to say that these two sentences can be true or false independently of each other. And now with entails, contradicts, and neutral, we have the three labels that are standardly used for NLI data sets at this point. Look at some additional examples. Some turtles walk, contradicts no turtles move. I think that's straightforward. Here's one that shows how intricate this could get. So the premise is James Byron Dean refused to move without blue jeans. Entails, James Dean didn't dance without pants. This highlights two aspects of the problem. First, you might have to do some complex named entity recognition on James Byron Dean and James Dean to figure out that these are co-referring expressions. And you also might encounter real linguistic complexity, in this case, emphasizing things involving how negations interact with each other. This next example begins to show how much common sense reasoning could be brought into the task. So the premise is Mitsubishi's new vehicle sales in the US fell 46% in June. And the hypothesis is Mitsubishi sales rose 46%. And we would standardly say that that is in the contradiction relation. Now, again, you might pause and think, it is certainly possible, even in our world, that Mitsubishi could see a 46% rise and fall in the same month. So surely these should be labeled neutral. But I think what you'll find in NLI datasets is that these are called contradiction on the informal assumption that the premise and hypothesis are talking about the same event. And in that context, we would say that these are common sense contradictions. Here's another example that highlights how much pragmatics could be brought into the problem. The premise is Acme reported that its CEO resigned, and the hypothesis is that Acme's CEO resigned. We would probably say entailment there, even though in a strict logical sense, the premise does not entail the hypothesis, because of course, the company could be reporting things that are false. But here we kind of make an assumption that the company is an authority and will likely report true things about facts like this. And therefore we allow that this would be in the entailment relation. Again, not logical, but much more like common sense. So just to emphasize this, here's kind of the fundamental question that we confront. Does the premise justify an inference to the hypothesis? Common sense reasoning rather than strict logic. Two other characteristics of this task in the modern era are, first, there's a focus on local inference steps, that is just one premise and one hypothesis, rather than long deductive chains. And the second is that the emphasis is really on the variability of linguistic expressions. When people have created the large benchmark tasks in this space, they have largely focused on just collecting a lot of data and not placed any special emphasis on collecting examples that have a lot of negations or quantifiers, or something that would really shine a spotlight on linguistic and semantic complexity. So that's worth keeping in mind about how we're thinking about the task in the present day. If you would like additional perspectives on this, including some disputes about exactly how to think about the problem and what would be the most productive, I would encourage you to check out these 3 papers by a lot of Stanford researchers. I think the fundamental outcome of this is that we do want to focus on common sense reasoning, even though that's a kind of amorphous and difficult to define concept. It's nonetheless arguably the useful one for us when we think about developing practical systems. Now, in a visionary paper that really set the agenda for NLI, Dagan et al. 2006, they make a lot of connections between NLI and the broader landscape of NLU. So let me just read this opening statement here. It seems that major inferences, as needed by multiple applications, can indeed be cast in terms of textual entailment. Consequently, we hypothesize that textual entailment recognition is a suitable generic task for evaluating and comparing applied semantic inference models. Eventually, such efforts can promote the development of entailment recognition engines, which may provide useful generic modules across applications. It's a wonderful vision, and the spin we might put on it in the present day is that what we might hope from NLI is that since reasoning about entailment and contradiction are truly fundamental to our use of language, that pre-training on the NLI task might give us representations that are useful in lots of different contexts. And Dagan et al. Actually continue by showing that we can formulate a lot of traditional tasks as NLI tasks. And here are just a few examples of that. If our task is paraphrase, we might say that in the NLI context, that means we want equality or mutual entailment between the text and the paraphrase, that is premise and hypothesis. For summarization, we would do something weaker. We would hope just that the text, the original text, entailed the summaries, allowing that the summary might be weaker or more general. For information retrieval, we kind of do the reverse. Here we want to find documents that entail the query. And then for question answering, it's kind of similar. We could formulate that as an entailment task by saying that what we want is to find answers that entail the question. And the way we might think about entailment for questions is kind of illustrated here, where we would informally convert a question like who left into someone left to give us a statement. And then we could say that Sandy left is an answer to who left in the sense that it entails someone left. And I think there are many other tasks that we could formulate in this way. And it does show you just how fundamental entailment and contradiction are to reasoning in language. And finally, let me give you a sense for the model landscape and how it has changed. NLI is a pretty old problem in the field, and as a result, we've seen a wide spectrum of different approaches. In the earliest days, you had a lot of systems that were kind of focused on logic and theorem proving. And I've characterized those systems here as offering really deep representations, but they weren't especially effective in the sense that they worked only for the domains and examples that the system designers had been able to anticipate. So they're kind of brittle. Following that, you have a kind of exploration of what Bill McCartney called natural logic approaches. Bill was one of the early innovators in this space. I think he actually coined the term natural language inference. And he explored natural logic, which has some of the aspects of logic and theorem proving, but is kind of more open and easily amenable to tackling a lot of data. And so those systems were consequently a little less steep, but also more effective. And a similar thing happened with the semantic graphs, which was providing rich conceptual representations of the underlying domain that we want to reason about. Another interesting thing here is that, until recently, it was the case that clever hand-built features, which I'll show you some a bit later in this screencast series, they were really in the lead. And simple n-gram variations, traditional models with hand-built features, they were the best models. There was a kind of faith early on in the deep learning revolution that eventually those models would prove to be the best at this task. But at the time, we just didn't have the data sets that would provide evidence for that kind of claim. And so as a result, for a while, deep learning systems really lagged behind these more traditional approaches. And I would say that it was really in about 2017 that deep learning pulled ahead. And that's a result of modeling innovations and also the arrival of some really large benchmark data sets that would allow us to train systems that were effective for the task. And it's at that point you see that deep learning kind of took over. And as a result, in subsequent screencasts, we too will be focused on deep learning architectures for the NLI problem.